unit of frequency was named, discovered an anomalous phenomenon that later became known as the photoelectric effect. It works like this. When light is shined onto a metal surface, the energy from the incoming electromagnetic waves gets transferred to the electrons in the metal. The electrons are initially bound to the metal, but the sudden kick in energy that they receive causes some of them to escape. We called these escaped electrons photoelectrons. The manner in which light behaved in the photoelectric effect was anomalous. It didn't seem to do what electromagnetic waves were expected to do. This experimental setup of the photoelectric effect involves a white light, which is composed of all frequencies of light, shining onto a metal, whose outgoing photoelectrons have their energies measured and displayed on the right. First, a red filter is placed in front of the light, which means that only red light is hitting the metal. The needle's position is at 0, which means that no electrons are being kicked out of the metal. The process is repeated, first with a yellow filter, then with a green one, and finally with a blue filter. Notice that in each case, the needle immediately jumps to a specific position on the energy measuring device, and that it stays there the entire time the filter is in place. This means that photoelectrons are immediately being kicked out of the metal the moment they get struck by the light, and that the energy with which they're escaping is not changing. Also notice that the energy increases as the filters emit electromagnetic waves with higher frequencies. This suggests that the energy of photoelectrons, and by extension the energy of the light waves that are knocking them out of the metal, is related to the frequencies of the incident light. To a physicist in the early 20th century, these results were a complete enigma. According to the wave picture of light, the photoelectric effect should occur at any frequency, but should rise with intensity. Yet experiments showed that the intensity of the incident light was irrelevant to how energetic the outgoing photoelectrons were. It doesn't matter how much red light you shine onto a metal. The photoelectric effect simply won't occur. On the other hand, you could shine a far less intense beam of ultraviolet light onto the metal, and the energies of the photoelectrons will be off the charts. This shows that the photoelectric effect is a sort of all-or-nothing process. Either light is energetic enough to kick the electron out of the metal, or it isn't. There's a quota of energy, the threshold energy, that simply isn't being met when red light is shining onto a metal. None of this was consistent with the behavior of waves. According to the wave picture of light, as more of these monochromatic electromagnetic waves were fired at the metal, the amount of energy that they released should have steadily increased as the incoming light rays combined their energies. Yet we clearly saw that the energies of the photoelectrons for each separate frequency remained constant. This characteristic is more akin to that of a stream of particles, where each individual piece of the light beam contains the same amount of energy, and thus releases the same amount of energy, as every other piece of light preceding and succeeding it. So if light is just a stream of particles, it follows that monochromatic light, having a narrow range of frequencies and thus a narrow range of energies, should yield a constant energy output, which is exactly what we observed. Finally, the wave picture of light predicts that there should be a buildup of energy prior to there being a photoelectric effect, due to the existence of the work function. The work function, whose empirically determined value varies with the type of material being considered, is the amount of energy needed by an electromagnetic wave to free an electron from the metallic surface. Basically, it's the threshold energy. According to the wave picture of light, if a light wave has low enough intensity, then the energy of incoming light beams should gradually build up energy until the energy of the light overcomes the work function, at which point the photoelectric effect may occur. Yet we observed that the photoelectric effect took place immediately. There was no need for a buildup of wave energy because, once again, individual pieces of light either were capable of knocking out electrons or weren't, and this capability was determined immediately. You could have a beam of red light shining from a spotlight, and it will never release a single electron from the metal, no matter how long you shine it on there. Then you could have a beam of violet light shining out of a little laser pointer, and the metal will immediately start shooting out electrons. From all this information, Einstein found that the maximum kinetic energy of each photoelectron, Kmax, equals hf minus phi, where Kmax is the maximum energy of an outgoing photoelectron, h is Planck's constant, f is the frequency of the light beam, and phi is the work function, which again depends on the material being illuminated. Now think again about what's happening during the photoelectric effect. Light, which has a certain amount of energy, is hitting an electron that has zero kinetic energy since the electron is stationary. If it transfers all of its energy into the electron, then the kinetic energy of the outgoing photoelectron is equal to the light's energy minus whatever energy was needed to free the electron. And this is exactly what the equation is saying. This term is the kinetic energy of the outgoing photoelectron, and this term is the energy needed to free it. So this term must be equal to the energy that the